Hi, and welcome to Demystifying Math. Today we're going to be working on improper integrals. An improper integral is one that has an infinite limit of integration, or it could have an infinite discontinuity within the limits of integration, or the infinite discontinuity could occur at the endpoints of integration. In today's lesson, we're going to be concentrating on improper integrals that have an infinite limit of integration. Let's look at an example. We're trying to find the integral from 2 to infinity of 1 over x squared. Well, that may seem kind of strange to you because we normally have numbers at the end points. With a problem with an infinity at the end point, we can still evaluate it by taking the limit as a particular variable goes to infinity, replacing our infinity sign with b, and then evaluating the integral. Now, all this may seem kind of strange to you because when we're trying to evaluate an integral, we're looking at the area under the curve. And in this case, the area under the curve goes out to infinity. But what happens with some of these functions is as you go toward infinity, the area under the curve is extremely small, almost insignificant. So we do approach a specific number for that area. And that's what we're looking for when we're evaluating an integral that has an infinity at the endpoint of the integration. Okay, so let's continue on. If we're going to evaluate the integral, we'll do the same thing as if we normally did, but then we're going to take the limit as b goes to infinity. So the integral of 1 over x squared is simply negative 1 over x, and then plugging in our endpoints at b and positive 2, we have negative 1 over b plus 1/2. Well, we got 1/2 because as b goes to infinity, negative 1 over b is going to go to 0. So we're just left with the 1/2. Now remember that this area is unbounded, but it does approach 1/2. And that's really what we're looking for here. Let's try to understand this a little bit better. Let's try breaking up a portion of the unbounded region into parts, and then find the sum of these areas. So looking at just the area from x equals 2 to 4. We want to find just this area. We can do that pretty easily with our integration techniques. So plugging in the 4, we get negative 1/4, and plugging in the plugging in the 2, we get 1/2. So we're adding it because there was a double negative there. And we're going to do the same thing for the region from 4 to 6. And again from 6 to 8. And again from 8 to 10. Then we would add together all these little areas. What you should notice is that if we added them all together, some things would cancel out. For instance, at the beginning we had negative 1/4. In the second integral we had plus 1/4, so those would cancel. Do you see what else is going to cancel out? The negative 1/6 and 1/6, the negative 1/8 and 1/8. And if we kept going out to infinity, what do you think we'd be left with? Well, we have 1/2 here. That's not canceling out. And whatever this last term is, we'll have a small number here. Notice as we go out toward infinity, this number is going to get smaller and smaller. So we're going to be left with almost nothing. So this area is approaching 1/2 as we go out to infinity. Okay? So let's try another one. This is going to be an improper integral that does not converge. What does converge mean? It means that it's going to a specific number. If it does not converge, we call it divergent. It means it's not going to a specific number. So let's look at what happens technically with the integral. This is going to be the function 1 over x, and we're going to try to integrate from 5 to infinity, which means that first of all, we're going to rewrite it as a limit as b goes to infinity. And then evaluate it. Well, of course, we know that the integral of 1 over x is the natural log of x. So that gives us a natural log of b plus a natural log of 5. Well, as b goes to infinity, so does the natural log of b. And it really doesn't matter that the natural log of 5 is a constant because we're still going out to infinity. So this is what we call a divergent integral. It's not going to a specific number. Let's do this one more time. Let's again break up the area into parts and see what happens. So we're starting off with the first region here from 5 to 10 of 1 over x. Well, I plug in my two endpoints, I get the natural log of 10 minus the natural log of 5. And I'm going to do that for each of these regions here, from 10 to 15, from 15 to 20, and from 20 to 25. And again, you should start seeing some things that are going to cancel out. For instance, we have the natural log of 10 minus itself, the natural log of 15, and the natural log of 20. Well, what's different about this one than the last one is in this case we're starting off with a negative of the natural log of 5. And we're going to add whatever number is left here. Well, this number is much bigger than the natural log of 5. And if I kept going, I'd get bigger and bigger numbers here that I would be adding to the negative of the natural log of 5, which means that this area is going to continue to increase. If you look at our curve here, you can kind of see that this curve tapers off very slowly, whereas on the previous one, it tapered off pretty fast, going close to 0 very fast. So even though both these graphs are decreasing, positive functions, both heading to 0, one converges and one diverges. So with 1 over x is diverging, and the 1 over x squared converged. I hope this helped you clear up any information you needed about improper integrals. And thanks for joining us here at Demystifying Math.